Hi students. In this video, we're going to talk about the next type of gas law or gas calculation, and that's Charles' law. Now that we've seen the effects of pressure and volume, we're going to look at one of the other parameters we can measure gases by, and that's temperature. And that's what Charles' law does. So essentially with Charles' law, you can think of kinetic molecular theory. With kinetic molecular theory, we had discussed that the speed of the molecules is directly proportional to temperature. As you increase temperature, things travel faster. Well, if we take that concept and we think of a balloon that's placed in cold water, the molecules of the gas particles are going to travel at a slower speed. Because they travel at a slower speed, they will not push on this balloon as much and they'll contain a smaller volume. If the gas particles are traveling at a higher speed with more force, they're going to push out the balloon to equalize the atmospheric pressure on the outside. The only way to do that if they're moving faster is to have to travel further to have the same number of collisions. So what Charles found is that volume is directly proportional to temperature. So if I increase temperature and I want pressure to stay the same, because the particles are traveling faster, I'm going to have a larger volume so that the collisions remain the same. Again, it's hard to see this mathematically in just an equation or a proportionality. So I'm going to rely on that simulation again. So I'll go back to the PhET simulation. I like this gas intros, and I already have it set up where if we take a look, what I'm going to do is I have a certain volume of 10 nanometers. Right now, there's no temperature and there's no pressure because I haven't put any gas particles in there. I'm going to quickly just put a bunch of gas particles in there. And now that gas particles are in there, we see that a pressure is exerted. Now I want to keep pressure constant, and I only want to see the effects of temperature and volume. So right now with these number of particles, they're colliding on the container, and I can see per 10 picoseconds, there's about 165 collisions. What's more important, at this temperature of 300 Kelvin and this volume, I have a pressure of 23.4 atmosphere. With Charles' law, we want to make sure that pressure is constant, like the atmospheric pressure that that balloon observed, and that the gas particles are the same. So the moles of the gas are constant, just like the gas particles in that balloon from the slide. So what I am going to do is I'm going to change the volume and see how that's going to affect the temperature to keep pressure constant. So if I take this container, instead of 10 nanometers, I go down to half that to 5 nanometers. I want to keep 23.4 atmospheres, but to do that, because again, pressure is related to the number of collisions, I have to make sure that the particles are moving slower. That way the collisions remain the same, even though I have a much smaller volume. The only way to do that is to decrease temperature. So I went from 300 Kelvin to 150 Kelvin. So when I halved the volume, I had to halve the temperature. I went from 10 nanometers to 5 nanometers for the volume. And now I went from essentially 300 Kelvin to 150 Kelvin. And again, you can play around with that. But what I'm seeing is there is a direct proportionality. When I halved the volume, I halved the temperature. So that's an important concept for us to understand. The other thing I want us to understand is with Charles' law, there's a very important thing that we have to take in consideration when we're doing temperature calculations. Notice in that simulation, when I halved the volume, I went from 300, the units were Kelvin, to 150 Kelvin, okay? Why is that? Well, we can deduce from volume and temperature measurements. So if I measure the volume and the temperature, and if I'm using degrees Celsius, I can get data. And we see that there is a direct proportionality here. As temperature increases, so does volume if pressure is to remain the same. And if I take my set of data points and I draw a straight line, I can extrapolate something very important. I can extrapolate when my volume would be 0. Now, this is theoretical, but what it allows me to do is instead of looking at temperature with negative values, it allows me to create an absolute 0. And that absolute 0 we've talked about in the past is the Kelvin scale. And Kelvin is whatever your degrees Celsius is plus 273.15. Why plus 273.15? If I extrapolate from the straight line when the volume would be 0, I get it at a negative 273 degrees Celsius. So to make an absolute 0 scale, an absolute temperature scale, if I have negative 273.15 plus 273.15, Kelvin would be 0, and there's my absolute temperature scale. It is just slits. They just slide it over negative 273.15. Now that is important. So for all your gas law calculations, whether it's Charles, ideal gas law, combine all the laws, you have to use Kelvin. So I kind of already talked about absolute 0, and the absolute 0 is essentially using that Kelvin scale. So can we do calculations for Charles' law? And again, we just saw that Charles' law is volume is directly proportional to temperature. So if I was to solve to put this on the same side, I would have V over T always equals V over T. And I have initial conditions and final conditions. If I read a problem, a balloon has a volume of 785 milliliters. That's my initial volume. And a temperature of 21 degrees Celsius, my initial temperature. If the temperature drops, so there's a change in conditions, there's a change in temperature, this is my T2. What is the new volume? I'm looking for V2. So let's think about this. The reason why we have to use Kelvin, if I plug in a 0 for T2, that's going to be undefined. You're going to get an error on your calculator. So we're going to use the absolute temperature scale, where we're going to add 273.15 to degrees Celsius. Now that denominator in this ratio will not be 0, and we'll actually get a number. The other thing is, we'll notice that as I decrease the temperature, right, if I want this ratio to stay the same, that means my volume's going to have to decrease because they're directly proportional. So V1 over T1 equals V2 over T2. That's Charles' law. I can rearrange that for volume. And now I have to plug in the temperatures for Kelvin. So remember, T2 was 0 degrees Celsius, and 0 degrees Celsius plus 273 gave me my Kelvin, which is 273. T1 was 21 degrees Celsius plus 273. And when I add those two, I get 294 Kelvin, which is plugged in here for my T1. If you don't want to rearrange this algebraically, you don't have to. You can plug the numbers directly in here and then solve for your V2, which is what you're looking for. So I hope this helps you understand Charles' law and how volume and temperature are directly proportional if we keep pressure and the amount of gas particles constant. And I really want to emphasize, not just with Charles' law, but for all gas laws, we have to change the temperature, whether it's Celsius or even Fahrenheit, to Kelvin. Thanks for watching, and look for my next video where I'll discuss how to combine both Charles and Boyle's law for the combined gas law.